Okay, you guys, so I sent you another set of notes because the ones that you had were missing these two examples. So we went straight from example 8 to example last, and there are secretly two other examples that somehow got omitted from your packet. So I want to go through these because all we did was differentiate a series, but you need to know that you can also integrate a series. So the way to do something like this, it says find a power series for ln 1 plus x. And now that doesn't look anything like the power series we've been working with, right? ln 1 plus x, what the heck? Well, this is a hint, and it's something that you guys know, but it goes back to integration. So ln 1 plus x, it's the integral of one of the series we already found, and it's the sister of Big Mama. So Big Mama was this one, 1 over 1 minus x. And that was 1 plus x, whoops, plus x squared, plus x cubed, blah, blah, blah. And then you wind up getting to the general term, or the squished form, as I love to call it, x to the n, is going from 1 to infinity. But the sister says, hey, substitute in negative x for x, and rewrite that series. So this is 1 over 1 plus x. Notice the similarity between that and this. We don't really know why we're doing this yet. So this is going to be an alternating series. 1 minus x plus x squared minus x cubed plus x to the fourth, blah, blah, blah. That should be an x to the fourth. And then it goes on, and you, in the general term, substitute negative x for x, just like we did in expanding it. This is going from 0 to infinity, and this should have been 0. My bad. To infinity. And then we broke that up. We said, well, to recognize that as an alternating series, typically you're going to say negative 1 to the n, x to the n. And some people say, well, why do I have to do that? You don't really have to do that. But what it does is it accentuates the fact that this is an alternating series. You've got that negative 1 that's going through and changing the signs. So the idea with this one is that you know how to integrate something like this, right? So if I take the integral, this is ln 1 plus x, which you guys know, which is so exciting because what that means is if I want to write that as a power series, all I need to do is integrate these term by term. And on the AP, they're going to say integrate and give me the first, whatever, 7 terms or 5 terms of the series for 1 over 1 plus x. And so you integrate it term by term, give the terms that result, and then show in general form what that looks like. So here we go. What I did was I wrote out, and I'm going to erase this because we already have it written, right? So I already have I could rewrite it, but that's kind of silly. So let me erase this beautiful red, if I can. And we'll leave the general term because we're going to be integrating that too. So let me make this go up a little bit. I will get rid of that and pick the pen color of my choice, which I love purple. Perhaps you noticed my hair is purple. We are going to integrate this guy term by term because that's going to give me the series that's going to generate a power series for ln 1 plus x, because we know that the integral of that is, and I'll write it up here just so that you remember it, the integral of 1 over 1 plus x. It's kind of hard to write on here, dx equals ln 1 plus x. Now, if we're doing a general integral, right, I don't have limits on it, I got to put the plus c. So that is so messy, I just must highlight it. So this is where we're going with this. The plus c will be important because we're going to have to figure out what value it goes through on the y-axis, right? And secretly we know ln 1 plus x is going to go through 0, 0. Now you can, or ln x, I'm sorry, ln x is going to go through 0, 0. Because remember, that graph looks like this. So ln x, oh dear, I am in error. I don't really want a highlighter because I just want to show you this. So here we go. And I'll do it in a different color this time, just for fun. I don't want a text pen because what that will do is it will put everything in text form, which I'm not too interested in. And I'm still in text pen. I just want a pen. Okay, so let's pick green. So ln x goes through 1, 0. So ln x plus 1 shifts that to the left, and it's going to go through 0, 0, right? So if I added 1 to x, this shifts it left 1 unit. So we're going to use that in just a second. So the integral of this, which is ln 1 plus x, is going to be the integral term by term. So the integral of 1 is going to be x. Integral of x is going to be, and it's negative, so negative x squared over 2, plus x cubed over 3, minus x to the 4th over 4, plus, and you can see the pattern. This is old stuff. It's fun. Fun calculus, because the rule is very simple. It's just add 1 to the exponent. So to this exponent, I'm going to add 1. So I'm going to say this is negative 1 to the n plus 1, which I really didn't need to do that part, right? Because it's still going to alternate. X to the n plus 1. And that is over. And like I said, we don't really need this n plus 1. It's just going to cause everything to alternate, which is nice. So let's keep that where it is. Just move this, oh dear. Move that guy over is what I was going to do. And we'll call that negative 1 to the n, x to the n plus 1. And the reason I'm doing that also is that I'm starting at 0. So if I don't just keep it n, I would have to start the series at 1, and that's fine. There's no problem with that. But I need to start out with something to the 0 power in order to generate this original series, and then from that, it's going to generate the ln 1 plus x. So I'll keep that to the n. This is the sum from 0 to infinity. And you got to think about the pattern that we just did. We added 1 to the exponent, and I'm going to divide by that new exponent, which is n plus 1. So we have the series. Put on a plus c. Sometimes we put the plus c at the beginning, just so it doesn't look like it's part of the fraction. But that's it. Now, we're going to want to know the interval of convergence for this, because notice it's a series for ln 1 plus x. That's not the same as the ones that we've been doing, where we were just busting out a series for 1 minus x, or 1 plus x, or 1 plus x squared. So let's do that. Now we know we already said c is 0, because if I do, if I graph it, ln 1 plus x on its own, it goes through 0, 0. So I'm not going to really have to worry about that. We'll put a plus 0 on it just for fun. I need to find the interval of convergence, the IOC. And you know that that means take this original guy, add 1 to each term, and that will give me my next term. And don't forget your limit notation. Essential, or you are lying, n is going to infinity, of the absolute value, and I'm adding 1 term to each one of these, so I get the next term. So negative 1 to the n plus 1, x to the n plus 1 plus 1, right, because I'm substituting that in, all over n plus 1 plus 1, and I'm going to multiply that by the reciprocal of the original. I'm really dividing it. I get this giant complex fraction, but I'm not interested in writing and rewriting, as you know. And we've been doing enough of these. This is negative 1 to the n, x to the n plus 1. We're looking for what happens if the limit goes to infinity, and notice again that only the n is moving, right? The x is acting sort of like a constant here. It's not doing anything, which is good, because then I will get what can x be. And this is the ratio test. I have to set it less than 1 because we're trying to force this series to converge somewhere. And the ratio test says if you do this limit and it's less than 1, it will converge, right? So let's do it. Now, the negative ones don't matter. That's why I could have put it in or not put it in. We're in absolute value land, so we don't really care about the negatives. Let's just rewrite this limit as n goes to infinity of, and I'm going to call this x to the n plus 2, obviously. I'm just simplifying that. N plus 1 is often known as n plus 2. On the top, I still have n plus 1, and I've got x to the n plus 1. I'm just making sure I got this right, n plus 1. Okay. And again, that's less than 1. And now I can cancel. You guys are canceling kings. N plus 1 into n plus 2 is going to leave an x on the top. So here's my x. The limit is n moving. N's getting gigantic. And I know that the ratio of the coefficients of n plus 1 over n plus 2 is 1 over 1. So I just wind up with x in absolute values. We've already taken the limit is less than 1. Now, Algebra 2 would suggest, your early childhood math, that this has to be between -1 and 1 in order for the absolute value to be less than 1. So far, my interval of convergence, I know the limits of it. It's -1 to 1. The question is, am I including or not including those endpoints? And we must test. So as you know, I'm going to test x equals -1. And over here, I'll test x is equal to 1. Okay. And we're going back to the series that we just generated. So it's this series. Let me see if I can highlight it in shocking blue. This series is what I'm dealing with. That's where I'm finding the interval of convergence, right? So instead of x, I'm going to put in 1 and -1. So we'll start with the -1. I just like to highlight. Okay. So let me go back to my pen. And I will grab the fabulous black. All right, so for n equals 1, sorry, -1, I got the sum of -1 to the n is still there. That will be important because you can't just ignore that. Let's see. X to the, in fact, this is -1 to the n plus 1 all over n plus 1. Oh, that's so messy. I'm starting at 0 and going to infinity. So that series is something where I can put these guys together. I can say this is -1, add those exponents to the 2n plus 1, and that's over n plus 1. And this is going to go from 0 to infinity. The question is, does that guy converge or diverge, and how do I know? Well, remember, if I had x to the 2n, that would be an even number, right? In this case, 2n plus 1 will cause this to be -1 forever. It's just going to be an odd number, -1 to the third, -1 to the fifth, -1 to the seventh, whatever. So I'm going to rewrite this as a simple -1 over n plus 1. It's still the sum and is going from 0 to infinity. It is not an alternating series, correct? In fact, this I could start at 1. So what if I did that? This is sort of sneaky smart. What if I started at 1? That would mean that I'm pushing this series back by 1. So it would be n minus 1 plus 1, right? So we're going back a term in order to get back to 0. And so what I wind up with is just -1 over n. And that should excite you and delight you because that's harmonic, right? It's harmonic and it diverges. So I know the left endpoint truly is -1 not included. So I can come back up here and say my interval is -1, not included for sure. My next one, so this is the sum from 0 to infinity, so I'm not changing that, of -1 to the n, x, times 1 to the n plus 1. So we are putting in n plus 1 for this. Actually, I'm not putting in n plus 1. I'm just rewriting it with a 1 instead of an x all over n plus 1. Now, -1 to the n is going to flip-flop, right? This is going to go positive, negative, positive, negative, positive. So this is an alternating series. And this n plus 1 on top does not matter, right? I don't care what I'm raising 1 to. So I'm just going to simplify this. -1 to the n all over n plus 1. It is the sum as n is going from 0 to infinity. And because it's alternating, I need to use the alternating series test. So I need to make sure that it's positive, which without the -1, it is positive. Yep. I need to know that it's decreasing. So without the -1, I'm going to put in n equals 1, 2, 3, 4, 5, and it's definitely decreasing. And I need to know if the limit of 1 over n plus 1, notice I'm still leaving off that -1. I don't care about that. Without the -1, I got to make sure that that goes to 0, and it does. The three conditions for alternating series are met. Alternating series says if those are met, the series converges. It's the only conclusion you can get for alternating. So it's going to converge by alternating series test. So if I come back up here, then I know that this right endpoint is included. Left endpoint was not. So my interval is from -1 to 1, not including, and then including those endpoints. Okay, so that's why that is a really important example, because without it, you wouldn't realize probably that you can integrate series. Okay, the next one from what you guys downloaded, I hope, is example 10. Now, example 10 seems to not work with any of these, right? I've got arctangent. Well, how is arctangent related to any of the series that we've been doing? Well, what if I did this? What if I integrated, because I know the integral of 1 over 1 plus x squared is arctan. Now, we already, that's supposed to be an x. That's extremely ugly. I think I had too much coffee today. Too much coffee. I need a pen. Purple is my friend. 1 over 1 plus x squared. All right, now we already did this earlier in the notes. So you can flip back and say, oh, that's right. 1 over 1 plus x squared. That was like a cousin of Big Mama. Wound up being 1 minus x squared. So remember, I was substituting x squared in for everything in Big Mama's sister, 1 over 1 plus x, which was alternating. I get x to the 4th minus x to the 6th plus x to the 8th minus blah, blah, blah. General term for this was -1 to the n, and then x to the 2n from 0 to infinity. And again, the 2n is going to cause the first term to be 1, which is what I want. Okay. Well, arctangent, we just said, was the integral of 1 over 1 plus x. So again, I'm going to integrate this series term by term, and then integrate the general term in the same way. And again, we're going to have a c value, and we'll talk about that in just a second. So this is now arctan x. So that's going to be x minus x cubed over 3, similar to what we just did, plus x to the 5th over 5, minus x to the 7th over 7. If I do that for my general term, I'm going to have the sum. -1 to the n is not affected. That's a constant. But x to the 2n plus 1, I'm adding, and then I'm going to divide by that new exponent, which is 2n plus 1. I'm still starting at 0, and I'm going to infinity. Pretty sweet. So I added 1 to the exponent, divided by the new exponent, which is the rule for polynomials. So there's my series. I have a c on here because this is an indefinite integral. There are no numbers on it. So if I were to write this, it would look just like that. Now the question is, what is the c value and what is my interval? So let's just investigate for a second. Arctangent, you remember the graph, looks like this. This is why all that trig you did in pre-calc was so important. There are horizontal asymptotes. This is a tangent graph turned on its side and limited in its original domain, which becomes its range. So this is negative pi over 2 to pi over 2. But this is saying, where does arctangent go through the y-axis? I'm looking for the c value. Well, just like the one we just did, it's going through at 0. So this is really 0 plus all of this. So I don't need to put the 0 on there, obviously. And now we need to look at the interval. So the interval of convergence, and again, this isn't just a regular old one that we could say -1 to 1 on. This is arctangent, so I have to be careful for this one and test endpoints, all the stuff that we've been doing. So this is what it looks like. It's the limit, n is approaching infinity, of the sum. And all I'm doing is adding n plus 1 to all of this, and then I'm going to divide it by the original, which is the same as multiplying by the reciprocal. So, and I don't need the sum. So let me get rid of the sum. I don't need that. I'm looking at the ratio of the next term over the original term. So let's do that. The limit of the absolute value, -1 to the n plus 1. And the reason I don't care about the -1 is that we're in absolute values anyway. This is a plus. Oh my goodness. How ugly is that? It should be n plus 1. Okay. X to the 2n plus 1 plus 1. So I'm substituting n plus 1 in there for n. All over 2, then you got a parentheses n plus 1, plus 1, multiplied by the original one, and I'm just going to flip it. So I've got 2n plus 1 over -1 to the n, x to the 2n plus 1 must be less than 1, forcing it to converge. And just like last time, -1s are irrelevant in absolute values. So I get to simplify everything that's left. I got limit n is going to infinity of 2, just kidding, x, 2n plus 2 plus 1 would be 2n plus 3. Bottom is also 2n plus 3, just simplifying that. And then I've got the 2n plus 1 still on the right top, all over x to the 2n plus 1. Absolute value needs to be less than 1 for it to converge. And then I get to simplify. This is kind of fun. 2n plus 1 and 2n plus 3 are going to leave x squared on the top. That's what I get left with on the top. 2n plus 3 over 2n plus 1, don't really care what that is. My n is going to infinity. This is going to 2 over 2, also known as 1. So I wind up with, everything is canceling. I just get the absolute value of x squared. So we took the limit, n's are gone, is less than 1. Okay, now you got to be careful with this. You can't just say x squared is in between -1 and 1. It might be, but you've got to use sign analysis for this. So if I were to pull that out of absolute values, x squared is less than 1. That means that x squared minus 1, don't forget the pre-calc that you know has to be less than 0. So factoring this, I get x plus 1, x minus 1, has to be less than 0. So I'm looking for, wow, I wrote 1. I'm looking for the interval where this quantity is negative. We want to know where is this whole thing negative. So you bust out a number line. You say my important numbers are -1 and 1. Pull this down a little bit. I don't know about the endpoints. So I'm going to leave it less than for right now and test those. So actually, let's test these guys first. So let's say I put in -2, 0, and 2. And I'm putting them back into here to find out, is it negative or positive? So if I put a -2 in there, that's going to be negative times negative is positive. Don't like that region because it's positive. I need it to be negative. If I put a 0 in there, I get 1, which is positive, and then I get a negative. So this becomes negative. If I put a 2 in there, I get positive times positive, which is positive. So I know my region has to be somewhere between -1 and 1. I wanted a blue pen. Somewhere between here. I just need to know the endpoints. I'm not sure whether to put open circles or closed circles, brackets, parentheses. What in the world am I doing? So let's test. We're going to test x is equal to -1. And then I'm going to test x equals 1. You got to show this stuff. So if x is equal to -1, I've got the sum from 0 to infinity. And I just use that series, the original series. So I've got -1 to the n. And then I'm putting in a -1. So I've got a -1 to the 2n plus 1 all over 2n plus 1. And I got to think about what's going on with this. Remember, this thing, the -1 to the n, is going to make it alternate. This is always going to be negative, right? So 2n plus 1 as an exponent for -1 will make it negative, 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 but then this alternates. So this is an alternating series. Oh, it's so ugly. Oh my goodness, series. And we got to make sure that the conditions that are required for alternating series apply, and then we can consider this a convergent part, this the -1. So here we go. Is it positive without the -1? Yes. Is it decreasing? Yes. Is the limit 0? So 1 over 2n plus 1. Is that limit as n approaches infinity 0? And the answer is why, yes, it is. So this one converges, oh my goodness, by, I'm glad there's audio for this. You can't read my writing. The alternating series test. So I know this part of the number line will have a bracket. It's included. Alternating series always concludes convergence. So this time let's test 1. I'll do it down here. Test x equals 1. And I shall do the same thing. I don't have any different thing for the -1 is part of the whole thing. So -1 to the n is still there. But then I get 1, because that's what I'm throwing in for x, to the 2n plus 1. Now, you know, if I just multiply or raise 1 to any power, it really doesn't matter. So all I wind up with is that first -1 to the n making a difference. I've got 2n plus 1 here. I'm starting at 0, and I'm going to infinity. So this is also an alternating series, right? I got to make sure that it is positive, that it is decreasing, and that the limit is 0. So the limit of 1 over 2n plus 1. Notice I'm ignoring the -1 that's flipping the signs back and forth. I don't care about that. I got to make sure that that's equal to 0. Oh, equals 0. So let me get rid of that. And then I shall check mark the ones that work. So this is equals 0. Why, yes, it's positive. It's decreasing. The sum is, or the limit is 0. So I'm going to also conclude it converges by alternating series test. So now I know that both of those endpoints are included. It will converge everywhere from -1 to 1, including the endpoints, which is kind of cool. So my interval of convergence is -1 to 1. Radius of convergence is from the center, which is 0, to either of those endpoints, which is 1. Done. Okay, so the last example we already did, that's this one. And inadvertently, I already did this one. because those other two were missing from your notes. So that's it. We spent 29 minutes and 58 seconds on this, which is mighty fine. So you guys can hopefully fill in your notes and then go have fun on this beautiful weekend. It's going to be nice this weekend, so have a great time. All right, I will see you in class.